Okay, so I start today's talk. So yesterday at the end, I talked about an MM bimodule for type 3 factor M, and I continue. So let M be a type 3 factor. So yesterday, I talked about some trivial bimodules. So they talked about bimodules a lot, but here so we have the left and the right algebra which are the same. So we have just one algebra M, both left and right. Then so here so we put the action of x and y of C defined by in this way. So this is a kind of trivial bimodule. So in the two-one factor case, this is just an L2 of M, and with the standard action from the left and from the right. But then take an endomorphism. Then we can define new bimodule H rho, the same Hilbert this original H. But the action is noun. So from the left we have the same action, but from the right we use this endomorphism first, and then so in this way. So the right action is modified with this endomorphism rho. Of course, so this the image is a subalgebra. So this really gives a commuting action from the left action. So this is an MM bimodule. So then so this makes sense for any factor, any fundamental algebra M. But an important fact for type 3 factor is that any bimodule is of this form. Up to some isomorphism. And this is because we have the following. So a particular fact about a type 3 factor is that any representation of M on the Hilbert space, which is assumed to be separable, any representation is I mean, all representations are unitarily equivalent. So, for the left action of M, we may assume that this is the standard form, just like this standard multiplication. Then, the right action of M must commute with the left action of M, which must be the action of M prime, so J something J. Then, this something must be an element of M, so from this fact, for any MM bimodule must be of this form. The left action may achieve the standard one. Then the right action must be of this form. Then this is a particular nice property of a type 3 factor. So this is not true for type 2-1 factor, but for type 3 factor, for any bimodule arises from an endomorphism. So study of bimodules is reduced to a study of endomorphisms. And in many cases, endomorphisms are much easier to handle now.
So you mentioned last time, so this J is defined in terms of a cyclic and separating vector. You mentioned it doesn't really matter last time. Can you say something about that? Like this, the choice of, you said, so there's unique representation, but
yeah,
but there's a choice, you're choosing a cyclic and separating vector to define the J.
Right.
So is there any difference at all?
No, I mean up to unitary equivalence.
Up to unitary equivalence, there's no difference.
There's a theorem of Iraqi which determines the J.
So in the order of this form. Then for two endomorphisms, H rho is isomorphic to H sigma for other MM bimodules. If and only if we have some unitary operator u, small u, in this type 3 factor M, such that a joint of u composed with rho is equal to sigma. So this gives a nice characterization when such bimodules are isomorphic. So this is one thing. Then also we can also identify the home space. So this is a space of homomorphism in the sense of MM bimodule. So it's a boundary linear operator from H rho to H sigma, which commutes with the left and right action. That's a notion of a homomorphism between bimodules. So this is an MM bimodule homomorphism. Then we can identify with this one T rho is equal to sigma T for N. So this T operator T, this is an operator in M, and this intertwines to endomorphisms rho and sigma in this sense. So this space of T is naturally identified with homomorphism, the home space of this one, and this we write this. So this is the home space for endomorphisms rather than bimodules. So then each law is reducible in the sense that we do not have a direct stamp decomposition of an MM bimodule. Then this is irreducible if and only if we have this one. So here we have the irreducibility if and only if we have only trivial intertwined trivial bimodule homomorphism. It means that here we have rho and sigma are the same. So rho x, T rho x is equal to rho of xt. So that means that commutant is equal to just the complex number field. So this is the reducibility of an endomorphism. So we say an endomorphism will be reducible if we have this trivial relative constant property. So we have notion of fusion, which Dave explained. So we have two bimodules. So this is a fusion of MM bimodules. So H rho tensor H sigma. So this is naturally identified with H rho sigma. So in this way, the fusion product of bimodule is identified with just a composition of endomorphisms and the fusion product is a rather complicated operation, but under this identification, this rather complicated operation is identified with a very simple notion of an of a composition of endomorphism. So this is one advantage to study bimodule using endomorphism. So this is about the fusion. And also we have a notion of direct sum. So for two bimodules, we can just take a direct sum as Hilbert basis. Then this gives us a direct sum of MM bimodules. Then, so we also have for H rho plus this is a direct sum of MM bimodule. H sigma is naturally identified with this one. Yeah. So this is this rho direct sum with sigma is a new endomorphism. It's defined in this way. So U rho of x U star plus B sigma x B star, where U, which way? U is so U here, U and V are isometric, and then with orthogonal range, so that the direct sum of the ranges is equal to the entire Hilbert space. And such U and V exist because we have a type 3 factor.
Economical generators of consalvator too.
Yeah, consalvator O2, yes. This is a standard consalvator. So in this way, we can define a direct sum. So this actually depends on the choice of U and V, but up to unitary equivalence, it doesn't matter. So in this way, we have the notion of direct sum. Then, for if dimension, sorry, the index is finite for an endomorphism, so the image of an endomorphism is automatically a subfactor, so we have such an index. Then we have irreducible decomposition. Of that is rho is equal to this is the final sum, where rho I is an irreducible endomorphism and then I is a multiplicity. Yes, non-negative integer. So this is the notion of irreducible decomposition. Actually, that corresponds to the notion of irreducible decomposition of bimodules, MM bimodules. Then,
if it's not integer, then there's a similar decomposition.
which is an integer?
The index.
The index. So this can be any finite number. It doesn't have to be an integer. We always have this kind of irreducible decomposition.
So the point is, irreducible ones don't necessarily have an index.
So I doesn't have to be an integer.
This is an index set, which is finite.
But not necessarily.
Ni is an integer, but
Yeah, this is
Rho
an
I
integer.
could have
This is a
an
multiplicity.
integral.
But I is not. I is not necessarily.
I can be.
It's just a labeling set, just
Yeah,
a set
it-
of colors.
Yeah, it's just a label not for finite.
I was gonna say that the main point is when Yasu, like, index, the row, but if even though the index there is finite, that doesn't mean it's an integer. It could be any.
Then it's more convenient to introduce the notion of a dimension of an endomorphism rather than the index of the image of an endomorphism. So for an endomorphism row of M, we set dimension of row. This is just, so we look at the Jones index of the image. So this is, but then, so this is not the dimension. Actually, we have to take a square root. Okay? And this convention is a more convenient number to deal with. Then we have dimension of row sigma, the composition of endomorphisms. This is equal, so this multiplicative.
Is this dimension always an integer?
No, this can be anything. So
Oh, no, the square root, as in.
so this index, it can be any real number, and we take just a positive square root. So this is a dimension, but so this is not an integer.
No, you told us yesterday it can't be any real number.
Oh, that's right.
But it's
Yes,
possible.
right. So there's the restriction theorem of Jones index. So
Oh, okay.
we take a square root. So this after 2, any valued particle between 1 and 2, it has to be the form
Oh,
2 cosine pi over n.
I forgot, yesterday we said that the finite possible indexes were the same for the infinite as well, right?
Excuse me.
Yes, okay.
Yeah, that's right. So this multiplicative multiplicativity holds, but okay, this is true without taking a square root. But the reason we took a square root is this one. For direct sum, after taking the square root, this becomes additive. This is ordinary addition. So, sorry. So this dimension can take non-integer value, but this really looks like a dimension of an ordinary representation, where this corresponds to a tensor product. So the tensor product of a representation, if we take a dimension for that, that's multiplicative. And also for representation for direct sum, the notion of dimension is additive. So something very similar to this situation, except for the fact that we can now take non-integer value. Okay. So this is the reason why we take the square root here. So this is a dimension of an endomorphism. Now, then we have to introduce the notion of a conjugate dimension. So H rho bar. So this already appeared in David's talk, but here we have to interpret this conjugate binomial in terms of endomorphism. So this should be isomorphic to H of rho bar. So this is an MN binomial, and by general theory, it must be of this form. So this must be some H rho bar for some endomorphism rho bar, but just from this, it's not clear what kind of endomorphism rho bar we have. So we have to identify this rho bar with something more concrete. That's the next page. Then, so, okay, so select n to be the image, so this is a subfactor. And this is on H row, just Hilbert space H. Then, so on this, we have, again, by the fact that we have type 3 factors, we have something very nice. So we have omega with this property. Actually, somehow redundant. So for this omega, we have this, so n omega or m omega or n prime omega, everything is dense in the Hilbert space. And in type 2-1 situation, such a vector never exists except for the trivial case where n equals m. But because we have type 3 factor, such thing happens. Then, so we can consider J. So we have two modular conjugation operators, Jn and Jm with respect to omega on the same Hilbert. Then gamma x is this one. So x is okay. So this is some operator acting on this Hilbert space. And then x is
There's a question.
yeah.
So we're just a little confused about omega.
So is this the unique vector which is
No, not
property,
unique.
or-
Omega is not
but
unique at all.
it exists. in
Yeah.
the type.
Actually, such omega makes a dense subspace, so we have a lot of choices. But so this gamma so actually depends on the choice of omega, but this unitary equivalent doesn't depend on the choice of omega. We can take any on such omega.
Is it generic? The omegas?
Yeah.
Is that how you get one for both M and N?
Yeah, yeah. So first we look at this definition, then we look at this part, JMXJM. Then from the property of the modular conjugation operator, this is in prime. So this is what I explained yesterday. Then for M is a larger algebra than N, so this implies a smaller algebra than N prime. Then we know that Jn so this is gamma of x. But then so this part is in N prime, so this is in which is N. Okay. So this gamma, the image of gamma of x is in N. Okay. So x is from the larger algebra, M, and we apply this gamma, and then the image is in the smaller algebra. Then we define bar is gamma. Because so gamma of x is in N, which is a row of M, so we can apply row inverse. Then so this is some endomorphism of M. And actually, this gives the conjugate dimension. This gives, proof, and this is not trivial at all, but we can prove that this is the conjugate binomial. So this,
Yeah, like row inverse, that it's, row is injective.
yeah, that's automatically injective because it's an endomorphism from a factor. So the kernel should be an idea which is massively trivial. Yeah, we can define row inverse. So this gives the conjugate bimodule, and so this gamma is rhombus, it's called rhombus canonical endomorphism. So the image is containing n, and actually the image is not equal to n. The image is strictly smaller than n, except for the trivial case where m is equal to n. So we have this thing. So in this way, we can define this following endomorphism. Then we have an important fact which is called Frobenius reciprocity. So let, okay, rho sigma, lambda, lambda mu, irreducible endomorphism. When such a factor is finite dimension. Then home space of there is some natural isomorphism. So we have home space from lambda mu, composition lambda mu to mu, but then we can move mu to this side. But then we get mu bar instead of mu. So from lambda to mu bar. Okay, so, this is called a Frobenius reciprocity because this is analogous to the classical result, which is called Frobenius reciprocity in the classical representation theory. So this refers to the tensor product of representation finite group or compact group. We have a similar in classical setting. Then we have the following. So that's a general setting, and we now start with the subfactor. Okay, type 3.
Frobenius reciprocity is only for SL2 representations. What's the analog here?
For SL2, I think that's for
It's
general.
not a group representation.
Yeah, for
Every finite
compact
group?
Yeah, finite group, yeah. We start with the type 3 subfactor n in m with finite group. Then, so in general, in this setting, n and m, these two factors may not be isomorphic, but in a typical situation, they are isomorphic. And for example, we are interested in the application to conformal field theory, and in that situation, as I said, if m is the Archimedes type 3 factor, then n is automatically isomorphic to m. So in a typical situation, these two algebras are isomorphic.
That's just m is 3-1 and n is finite index n is 3-1.
I mean, yeah. Well, it finds type 3-1 and finite index, the other is also type 3-1. And there are lots of different type 3-1 factors, but if we consider the Archimedes type 3-1 factor, then the other must be also the Archimedes type 3-1 factor. So if they are,
And that's true both ways, if n is
Yeah.
3-1.
yeah.
And you need like Hagroth's classification for that?
Yeah, that's right. So that's we use it for the injective type 3-1 factor. they are isomorphic. So in particular, we have the isomorphism from M onto N. That's actually an endomorphism. Oh, yes. So the above setting of considering endomorphism is sufficiently general to study such a subfactor. So we may assume that any subfactor of finite index arises from an endomorphism.
Is it true for type 3 lambda as well? For the hyperfinite type 3 lambda factor and finite index subfactor, is it the same? Is it hyperfinite?
No, it could be say type 3 lambda squared. But except for some such rather trivial situation, they are. So we start with this setting. So now we have an endomorphism rho. Then we consider a sequence of endomorphisms. So we start with the identity and automorphism, which is also an endomorphism, and that gives a subfactor of index 1. Then we start with rho, then we consider rho bar. And rho bar. So we multiply rho and rho bar alternating in this way. And okay, I forgot to say that we have the dimension of rho bar is equal to dimension of rho. So each endomorphism is a composition of finite dimension endomorphisms. So each is a finite. Each has finite dimension. So each has a reducible decomposition. And then we can draw the following. Then so we start with identity, which is non-endomorphism, which is irreducible. Then we draw the next one, rho, which is typically irreducible. Then next one, rho bar, which is never irreducible except for the index 1 case. Then we have some actually identity appears here because of Rabin's reciprocity. And then we have something here, and then we have something. Here. So we have this kind of graph, and for each vertex represents an irreducible endomorphism, and the H is given up by the following rule.
Is each level of the graph one of the things in this sequence? Each like vertical, like horizontal level is one of the things in this sequence of endomorphisms.
Yeah, right. So this is So this is the identity, and this is the row. And this is the decomposition of row bar. And this is row bar, row. And this is row bar, row. So in this particular example, this endomorphism is decomposed into 3 irreducible endomorphisms. And then, when we go one step down, so it means a multiplication by row bar or row from the right. Then, for lambda, we have this kind of picture. So we have lambda of row is say lambda 1 plus 2 lambda 2 plus 2 lambda 3. So if we multiply a row from the right to this lambda, and then we make an irreducible decomposition. And if we have lambda 1 plus 2 lambda 2 plus lambda 3, we have three irreducible endomorphisms, then we draw edges like this 1, multiplicity 1, so we have 1 edge here, we have 2 here, and we have 3 here. Sorry, one edge here. So this kind of thing. Then from any reciprocity, so graph for each. So we look at this graph, this part. So graph between graph the first step and then nth step is reflection of the graph between n and n minus 5 steps plus something. And this something could be executed. So in this situation, so okay, so we have this graph, just one edge here. Then so this we make a reflection here. So we have some this part is a reflection of this one. Then we have plus some new thing like this part. And then so this part next step is so here we have these two edges. Okay, and so we have a reflection here. So this part is a reflection of the previous step. Then we have some new graph like this. Then here again we have a reflection of this one. And then a new part. And then here we don't have a new part anymore. Everything is a reflection of the previous step. And again we have no more. So this part is the new part, so plus something of the new part. And so this new part could continue infinitely. So we look at only new part.
So in the graph, what is the difference between row and row bar?
Excuse me?
In the graph?
Yeah.
How do you distinguish between row and row bar?
So
The stuff that is the stuff that's not a reflection of the
So row bar doesn't appear in this part. So each step we multiply row bar or row alternately. and then mimically reduce the decomposition. So some end notions here. Then for each step is a reflection of the previous part plus possibly new part, and we look at only the new part. So then we get some graph of this type.
We also do the same thing starting with row bar. So there's
Yeah,
a second
okay.
graph with a row bar.
Then we just look at the graph consisting of the new part. This could be which could be but then, so this graph is called the principal graph actually for traditional reason. This is a dual principal graph. This graph. So here we have some adjective dual, and this is because of the following. We can repeat the same procedure for the sequence. So we start, first we multiplied from the right by a row, but now we can use row bar. So we multiply row bar and row alternatively, and then we can repeat the same procedure and we get some graph. Then the graph arriving. The graph consisting of the new part. It's called the principal graph. So in this formulation, this dual principal graph appears more naturally, but for historic reason, so Jones considers this one first. So the name, we use the name principal graph for this one, and we call the dual principal graph for the other one. They are really paired, so it doesn't matter so much.
Can we play with this as a graph and remembering the layer of each vertex? Remembering like the height and
So
upper
here,
layer.
so here, for each step we have alternating multiplication. So this is really a bipartite graph. So we have a distinction of the even vertices and odd vertices. So here I have this graph, but this part can be written also in this way.
I remember the initial vertex as well in calc.
So we have 1, 2, 3, 4, 5, 6 vertices, and here this we have this is an even vertex. Here we have this is an even vertex. This is an even vertex. And here we have multiple vertices, and they are here. These are bipartite.
Bipartite means it's sound bicolored, or
Yeah, bicolor. So the vertices are colored in black and white.
and they don't sit next to each other.
Right, so we have no edge between phase y.
Initial star, okay.
So we have two graphs. So actually, if one of the two graphs is finite, then the other is also automatically finite. And we are particularly interested in this case where we have this kind of finiteness. And in this case, we say a subfactor is of finite depth. And this name depth comes from this kind of picture. So this is depth. We stop at the finite depth here. We do not go to infinite depth. That's the reason why we use this terminology. And we are particularly interested in this position. The theorem is it is due to many people, but maybe it is not here. So if index is less than 4, so recall that the index value 4 is a special value. Up to 4 we have discrete value, only discrete values, and after that we have anything. So if we have an index value below this critical value, then we automatically have a finite depth. And the path through principal graph. Linking diagrams. Of type A and also B even and E6 and E8. Okay. So the AN graphic is kind of things. Just one straight line. So D has a fork at the end. And the 2n means that, so in general, we have a linking diagram Dn where we have n vertices. But here we have even number, so it means that we have only even number of vertices. That will be 2n.
Where does this restriction come from?
That's difficult. This requires a lot of difficult work.
And same for E7 also.
E7 doesn't appear. Also, D8 doesn't appear.
So then you could ask why it doesn't appear.
Yeah, so of course we have proof, but that's not so easy to explain. So the E6 is six vertices. So that example is actually E6 and the 1.1. So in the ordinary thinking diagram classification, we also have the odd and seven, but they do not appear somehow. So that was a very surprising fact at the beginning. But today, so this was found in late 80s. So today we have and also the two graphs are the same. The principal graph and the dual principal graph are the same.
The principal graph determines the inclusion.
Hmm?
The principal graph, does it determine?
No, but so I now explain that. So the principal graph itself does not determine the inclusion uniquely, but there are some extra data. Then we can recover the subfactor. So next year I explain the problem you mentioned. We are often interested in classification of subfactors. And then for general factor classification is hopeless. We have lots of weird subfactors. But if we restrict ourselves to the so-called hyperfinite case, they are not appearing in this. That is a factor which is approximated by an increasing sequence of finite dimensional subalgebra, a so-called hyperfinite. So type 2-1 or type 3-1 factor. So they appear in the infinite tensor product construction. So we are interested particularly in this situation, and also particularly in the 3-1 case and in the conformal theory. So then n is automatically isolated to this one. If we have a finite index, then the theorem of Popper. So the two graphs, a principal graph and the dual principal graph. Okay, suppose we have finite. This is an important assumption. Then the two graphs plus some cohomological data. Determine, recover the original subfactor. So the graphs alone do not recover the subfactor uniquely, but if we have some extra data, which is of cohomological nature, we can recover the subfactor, and also we have a precise form what we mean by this cohomological data. And I just mentioned that this set of cohomological data the same information as the two categories generated by m. So we have m as an m bi-module, but actually we have L2 completion, or Hilbert space completion, but we can have n bi-module arising from subfactor. Then through the fusion product and reducibility composition, this generates some kind of category, two category in the sense they explained. And actually this category has the same information about this homological data. So from this information on two categories, we can recover the subfactor completely. That's the meaning of this Hopper theorem.
So what are the objects in the two categories?
Okay, so the objects are just n and n.
Just n?
Yeah.
Okay.
So we have only two algebras here. And then, then we have the binomial arising from this. So, in this way, some motion of tensor category naturally appears in subfactor theory. So today I stop here. Thank you.
Any questions or comments?
Is there a relation between the norm of the graph and
Yeah.
the dimension?
Yeah. Actually, so for each graph, we have the adjacency matrix, and then we have notion of norm. And actually, the norm is the square of the norm is equal to the joint index.
So the dimension.
Yeah. And this is one way to get a restriction. So, if the index is below 4, the dimension is below 2, and this is, has to be the norm of some adjacency matrix, then classically it's known that only an ADE diagram can pass.
Yes.
So in this way we get the restriction, but still we have to work on that exclusion of D order D7 and also realization of the other.
So, Janos, the M and N are just any subfactors? That is not necessarily one?
Okay, it can be any. Okay. So if M and N are any factor, then we still get this restriction. So the principal graph must be one of them. That's always true. But for realization of all these graphs, we need hyperfinite. So the factor should be this special thing.
Any more questions? If not, thank you again.
Thank you.